Hello and welcome everyone to Sciencera. In this video, we are going to discuss amines from Organic Chemistry CHE1502 module. I will be using Organic Chemistry by LG Wade, 7th edition. So let's begin. Introduction. Biologically active amines. Amines are organic derivatives of ammonia with one or more alkyl or aryl groups bonded to the nitrogen atom. As a class, amines include some of the most important biological compounds. Amines serve many functions in living organisms such as bioregulation, neurotransmissions, and defense against predators. Because of their high degree of biological activity, many amines are used as drugs and medicine. Some examples of active amines include dopamine, epinephrine, L-tryptophan, histamine, pyridoxine, nicotinic acid, and piperazine. Alkyl- Alkaloids are an important group of biologically active amines, mostly synthesized by plants to protect them from being eaten by insects and other animals. The structures of some representative alkaloids are shown here on the diagram. Nicotine, which is used in tobacco, and conine, which is used in poison hemlock. Although some alkaloids are used medicinally, chiefly as painkillers, all alkaloids are toxic and cause death if taken in large quantities. Classification of amines. Amines are classified as primary, secondary, tertiary, or quaternary. Primary has one alkyl group bonded to the nitrogen. Secondary has two alkyl group bonded to the nitrogen. Tertiary has three alkyl group bounded to the nitrogen, and quaternary has four alkyl group bounded to the nitrogen, and nitrogen bears a positive charge. Example of primary amine include cyclohexylamine. Example of secondary amine is piperidine or N-ethylalanine. Tertiary amine is N,N-diethylanilene, and the example of quaternary amine include tetraethylammonium iodide. Nomenclatures of amine. Common name. Common names of amine are formed from the names of alkyl group bonded to the nitrogen followed by the suffix amine. The prefix di, tri, and tetra are used to describe 2, 3, or 4 identical substituents. In naming amines with more complicated structure, the NH2 group is called amino group. It is treated like any other substituent with a number of other symbols indicating its position on the ring or carbon chain. Tertiary and secondary amines are named by classifying the nitrogen atom as alkyl amino group. The largest or most complicated alkyl group is taken to be the parent molecule. Aromatic and heterocyclic amines are generally known by historical names. For example, phenylamine is called aniline. For its derivatives are named as derivatives of aniline. For example, N,N-diethylanilene. Nomenclature of amines using IUPAC name. The IUPAC nomenclature for amines is similar to that for alcohols. The longest continuous chain of carbon atoms determine the root name. The E ending in alkane name is changed to amine, and a number shows the position of the amino group along the chain. Other substituents on the carbon chain are given numbers, and the prefix N is used for each substituent on the nitrogen. Examples of amines include 2-butane amine, 3-methyl-1-butanamine, N-methyl-2-butanamine, and so on. Structure of amine. We saw that ammonia has a slightly distorted tetrahedral shape. A lone pair of non-bonding electrons occupy one of the tetrahedral position. This geometry is represented by sp3 hybridization of nitrogen with the bulky lone pair compressing the nitrogen and hydrogen-hydrogen bond angle to 107, which is less than the ideal sp3 bond angle of 109.5. Trimethylamine shows less angle compression because the bulky methyl group opens the angle slightly as shown in the figure. The electrostatic potential map for trimethylamine shows how the non-bonding electron give rise to a red region, high negative potential above the pyramidal nitrogen atom. A tetrahedral amine with three different substituents and a lone pair is non-superimposable on its mirror image and appears to be a chiral center. In most cases, however, we cannot resolve such an amine into two enantiomers because the enantiomers interconverts rapidly. This interconversion takes place by nitrogen inversion, as shown in the figure, in which the lone pair moves from one face of the molecule to the other. The nitrogen atom is sp2 hybridized in the transition state and the non-bonding electrons occupy a p orbital. This is a fairly stable transition state as reflected by a small activation energy of 25 kilojoules per mole. Interconversion of R and S ethylmethylamine occurs hundreds of times per second at room temperature. In naming the enantiomers of chiral amines, can in gold preload convention is used, with non-bonding electron pair having the lowest priority. So, when describing the structure of amines, we need to remember three important things. Nitrogen is sp3 hybridized with lone pair of electron, bond angle is less than 109.5, and nitrogen may have three different groups and a lone pair, but enantiomers cannot be isolated due to the inversion around. Although most simple amines cannot be resolved into enantiomers, several types of chiral amines can be resolved. Amines whose chirality stems from the presence of asymmetric carbon atoms, most chiral amines fall into this group. Nitrogen inversion is irrelevant because nitrogen is not chirality center. For example, butane 2-amine can be resolved into enantiomers because the 2-butyl group is chiral. Second point is quaternary ammonium salt with asymmetric nitrogen atoms. Inversion of configuration is not possible because there is lone pair to undergo nitrogen inversion. For example, the methyl ethyl isopropyl anilinium salt can be resolved into enantiomers. Another point is amines that cannot attain the sp2 hybrid transition state for nitrogen inversion. If the nitrogen atom is contained in a small ring, for example, it is prevented from attaining the 120-degree bond angle that facilitates inversion. Such a compound has higher activation energy for inversion. The inversion is slow and the enantiomer may be resolved. Chiral aziridines, three-membered ring containing a nitrogen, often may be resolved into the enantiomers. Physical properties of amines. Amines are strongly polar because the large dipole moment of the lone pair of electrons adds to the dipole moment of carbon-nitrogen and hydrogen-nitrogen bonds. Primary and secondary amines have nitrogen-hydrogen bonds, allowing them to form hydrogen bonds. Pure tertiary amine cannot engage in hydrogen bonding because they have no NH bonds. They can, however, accept hydrogen bonds from molecules having OH or NH bonds. Because nitrogen is less electronegative than oxygen, nitrogen-hydrogen bond is less polar than the OH bond. Therefore, amines form weaker hydrogen bonds than do alcohols of similar molecular weight. Primary and secondary amines have boiling points that are lower than those of alcohols, yet higher than those of ethers of similar molecular weight. With no hydrogen bonding, tertiary amines have lower boiling point than primary and secondary amines of similar molecular weight. All amines, even tertiary ones, form hydrogen bonds with hydroxylic solvents such as water and alcohol. Therefore, amines tend to be soluble in alcohol, and the lower molecular weight amines up to about 4 carbon atoms are relatively soluble in water. Perhaps the most obvious property of amines is their characteristic odor of rotting fish. Some of the diamines are particularly pungent. Two examples of those pungent diamines include putrescine and cadaverine. Basicity of amines. An amine is a nucleophile Lewis base because its lone pair of non-bonding electrons can form a bond with an electrophile. An amine can also act as Bronsted-Lowry base by accepting a proton from a proton acid. Because amines are fairly strong, their aqueous solutions are basic. An amine can abstract a proton from water, giving an ammonium ion and a hydroxide ion. The equilibrium constant for this reaction is the base dissociation constant Kb for the amine. The value of Kb is fairly small, up to 10 to power minus 3 or even smaller, and the equilibrium for this dissociation lies towards the left. Nevertheless, aqueous solutions of amines are distinctly basic and they turn litmus paper blue. pKb value to compare the relative strength of amine as proton bases. Stronger bases have smaller values of pKb. Strongly basic amines has a weakly acidic ammonium ion and a weakly basic amines has a strongly acidic ammonium ion. Factor that affects amine basicity. The figure shows an energy diagram for the reaction of an amine with water. On the left are reactants, the free amine and water. On the right are the products, the ammonium ion and hydroxide ion. Any structural feature that stabilizes the ammonium ion relative to the free amine shifts the reaction towards the right, making the amine a stronger base. Any feature that stabilizes the free amine relative to the ammonium ion shifts the reaction towards the left, making the amine a weaker base. Factors that affect amine basicity. Substitution by alkyl group. An example, consider the relative basicities of ammonia and methylamine. Alkyl group are electron donating towards cations and methylamine has a methyl group to help stabilize the positive charge on nitrogen. This stabilization lowers the potential energy of methylammonium cation, making methylamine a stronger base than ammonia. The simple alkyl amines are generally stronger bases than ammonia. Resonance effects on basicity. Aryl amines are much weaker bases than simple aliphatic amines. This reduced basicity is due to the resonance delocalization of non-bonding electrons in the free amine. Figure shows how stabilization of the reactant, the free amine makes the amine less basic. In aniline, the overlap between the aromatic ring and the orbital containing nitrogen's lone pair stabilizes the lone pair and make it less reactive. This overlap is lost in the anilinium ion, so the reactant aniline is stabilized compared with the product. The reaction is shifted towards the left, and aniline is less basic than most aliphatic amines. Resonance effect also influenced the basicity of pyrrole. Pyrrole is a very weak base with pKb of about 15. Pyrrole is aromatic because the non-bonding electron and nitrogen are located in p orbital where they contribute to the aromatic sextet. When the pyrrole nitrogen is protonated, pyrrole loses its aromatic stabilization, therefore protonation on nitrogen is unfavorable and pyrrole is a very weak base. Lastly, we are going to look at the hybridization effect. Our study of terminal alkynes shows that the electrons are held more tightly by orbital with more s character. This principle helps us to explain why unsaturated amines tend to be a weaker basis than simple aliphatic amines. In pyridine, for example, the non-bonding electron occupies an sp2 orbital with greater s character and more tightly held electrons than those in the sp3 orbitals of an aliphatic amines. Pyridine's non-bonding electrons are less available for bonding to a proton. Pyridine does not lose its aromaticity on protonation, however, it is a much stronger base than pyrrole. The effect of increased S character on the basicity is even more pronounced in nitriles with sp hybridization. For example, acetonitrile has a pKb of 24, showing that it is very weak base. In fact, a concentrated mineral acid is required to protonate the acetonitrile. This brings us to the end of chapter amines. Hope you like this video. Thank you for watching. If you like this video, don't forget to subscribe for more.